My name is Nicholas Lee, and I'll be presenting the structural analysis performed by my project 2 for the final presentation. For my presentation, I'll be using a semi-monocoque sounding rocket called the NX-4 Spearling, designed for atmospheric research on an exoplanet that is 3 times denser than Earth's atmosphere. To accommodate these loads, I will incorporate a 6061 T6 aluminum skin and frames alongside a 2024 T3 longitudinal stiffener arranged around a 2.5 diameter cylindrical shell. This structure includes 8 hat stiffeners remaining closely spaced about 0.065 inches apart from each other. The critical loading case will be about 4G ascent at a 20-degree flight angle, which would include combined axial and bending loads through the cylindrical shell. Through our calculations, we found that the buckling and crippling results were able to show us something through what we wanted to find. And the skin panel buckling would be ending up to be around 1.12 KSI, where buckling is to be expected, alongside column buckling about 40 KSI, crippling to be about 38 KSI, and the peak compressive demand to be about 35.7 KSI. This confirms that the stiffener crippling, not material yielding or global buckling, would be the dominant structural limitation through the ascent loading. Next, we were able to move on to the lumped area versus the finite element results. To evaluate the structural response, 2 methods were applied: the lumped area for preliminary sizing and the Patran/Nastran finite element model for verification and refinement. For the lumped area results, we were able to gather an ultimate axial stress of 13.4 KSI, alongside a max compressive stress about 35.7 KSI. And then we were able to have a maximum tensile stress of 8.93 KSI as well. For the FEA results, this used the program in order to further and better match predicted results that we would possibly see inside the model. We had peak stresses that ranged from 38 to 42 KSI at the base stiffeners, while we ultimately saw a 0.42-inch deflection versus a 0.38-inch deflection in the Patran versus the analytical work. And ultimately, we were able to see that the structure maintains a slightly positive margin of safety despite the higher local stress magnitudes with like versus the lumped area predictions. This was able to see like a decent, strong agreement in the overall stiffness. And while this comparison does show that the lumped area provides more of a simplified estimate, it can also accurately capture like overall structure behavior and also correctly identify a governing failure, which was in our case the stiffener crippling. The FEA improved this accuracy by also accounting for detailed load paths and member interactions, confirming that the preliminary hand calculations did form a reliable foundation for our full finite element verification and analysis.